Catalyst Network has been designed as a new core protocol. The main driving force of designing this new protocol was to solve the blockchain trilemma, which is based on security, scalability, and decentralization. The other design rationales that went into building this system was to lower the barrier entry and to build a modular system. And the idea behind that was to make it flexible and ultimately aid the actual disruption. The Catalyst network consists of many different properties as a whole. So what we built is a new, what we call a probabilistic BFT consensus. It features what we call the DFS. It includes something called the distributed compute system. The distributed compute system is kind of a new terminology compared to stuff like limited smart contracts. The compute system allows much more complex computations to be done and then fed back into that consensus mechanism. Distributed DNS, the KVM smart contracts, and public and confidential transactions. So what is a probabilistic BFT consensus? The best way of describing that is a collaborative process in which nodes collectively vote on the global state transition of the entire ledger. So what I'm going to do is I'm going to kind of walk through that process of how you would produce a transaction and broadcast it to the network and ultimately achieve consensus. So this is our transaction object. What you can see here is that the main box on the left-hand side is what we call a protocol message. This is kind of like a packet in the Catalyst network. You can see the peer ID, correlation ID, message type, signature. All of this kind of stuff tells the packet how to get to different nodes and who sent it. What you can then see is a transaction message. We have this concept of entries in the ledger. So when you broadcast a transaction, you can broadcast a transaction that actually sends multiple transactions to people at once. And it could also contain public entries, confidential transactions, as well as smart contracts data. And then you can see a little bit more detail here about what actually is in the public entry. So it's quite standard here, to, from, transaction fee. On the contract entries, you have the amount and the call data, the data actually you want to call to the smart contracts. And then we've got this big bit of information here, which is the confidential entry. This is all designed around bullet proofs and range proofs. So we don't hide who the transactions go to, but we do hide the amount. You might not want to be telling people how much money you're getting earned. If you're wanting to pay an employee a salary, you don't want to necessarily disclose that to the entire world. So once you've made this transaction, we then broadcast it to the network. This is kind of very standard gossip protocol mechanism. So there's nothing too strange here in terms of how a blockchain works. But next up, we have something that we call the deterministic mempool. And if you remember what I said earlier on, this consensus is all based around people who are having to agree on a common set of transactions and come to an agreement on how the global state is to be updated. So we build a deterministic mempool, so everyone across the network should have the same set of transactions, and they should have the same set of transactions in an agreed order. And it's kind of a simple algorithm that we do. We order them by highest amount, highest fee, oldest timestamp, and then signature alphabetically. So as you'll see in here, just a very brief overview of how a deterministic mempool looks like. You've got the guy here that sent a transaction of 10 coins. So he's obviously got the highest amount. He comes first. You've got an amount there of 7 and 7, but this guy paid a fee of 3, and the other guy paid a fee of 2, so the guy with the high fee comes first. We're missing the timestamp one, but again, timestamp. And then these two guys have an amount of 1 each and a fee of 2 each, but this guy's signature is actually A, starts with A, and this guy starts with B. So the idea is that everyone should be able to come to an agreement on how to order these transactions. Obviously, some people might not receive some transactions, but this is accounted for later on in the consensus. So now we have all received these transactions, and now we've all got these transactions ordered. How do nodes actually come to actually validate the transactions? So maybe we talk a little bit about how these nodes are actually behaving on the network. all nodes or peers on the network have the concept of having 4 states while they're on the network. You can either be just a passive node. A passive node is just someone who's connected to the network. They could be wanting to create transactions, broadcast transactions, relay transactions to other people, but they could also just be people who want to interact with the services of Catalyst Network. You could just call them an observer, essentially, of this network. We then have what we call a reservist node, and that is someone who is signaled their intent to be able to join the validation pool. At this point in time, they're not necessarily validating transactions, they're solely there waiting to be admitted into this pool. It's kind of like the analogy of a nightclub that, you have a nightclub and then you have a queue outside, and as people come and leave, they'll get admitted into that pool. Next, we have what we call a worker node, and a worker node is someone who has been admitted into the club and is in that validation pool, but that doesn't necessarily mean that they are validating transactions. That is just someone who has the ability to validate. And next up, we have what we call a producer node. So this is the 4th state within the network. And a producer node is a subset of the entire worker node pool, or the validation pool. And this is the node who actually does validate transactions and is eligible to produce what we call a ledger state update. How do we actually select from the nodes that are worker nodes to be actually being a producer node? Again, kind of a very simple algorithm on how we actually select that subset each ledger cycle. So what we do is we take what we call a DFS hash, and the DFS hash is to do with the distributed file system of the network, and when we actually store the ledger state update, we put it into a distributed file system. That ledger state update is content addressable, so we actually hash the value of that state update, and that will give you a deterministic value across the whole network. So given a hash of a given delta for one cycle, we take an XOR distance between the key space of the content hash of that delta and of all the peer IDs within that worker pool. And we take X number of peer IDs that are closest to the previous delta hash, and that gives us a pseudo-random network-wide selection mechanism for selecting people who actually are able to produce the next state update. So this is kind of like it's kind of a little bit of an abstract view of the entire constitution of what we call the network. As you can see, the largest number of nodes in the network are the passive nodes, just people connected, relaying transactions, observing, interacting with services. We then have a smaller group, which is the reservist nodes, people waiting to be admitted into that queue, or into that pool, sorry. Then we have the worker nodes who are in that validation pool, and then a smaller subsection of actual producer nodes who are validating. This is all quite important. This all plays into the probabilistic nature of how you actually get selected and how you are actually able to produce a state update. So we've talked about this worker pool. The worker pool is, like I say, it's just a random selection of nodes in there. And between ledger cycles, as I explained earlier, random nodes are elevated into the producer cycle. So as you can see, between cycles, random nodes are selected. There's no real way of gaming this selection process. I mean, a large number of nodes, or say, for example, a botnet could come onto the network and try to pollute that worker pool. But the mechanism of actually signaling your intent to become in that pool actually depends on staking some coins. So there's actually a monetary value to actually become part of that pool, and that acts as a deterrent to people. So you mean if there's a worker pool of 50,000 nodes and you want to try and get 51% of that, you'd need over 25,000. If there's a monetary value there, that could actually provide a deterrent to people actually being able to, monetarily be able to admit it into that pool. But as I said, there's evil nodes in the world, there's evil people, like this guy, he's an idiot. But again, that probabilistic nature, if you're randomly selecting reservists every cycle, you're randomly selecting nodes, you've only got a very small probability of actually being selected into the producer cycle. So even if a few bad nodes do get selected into that given cycle, it doesn't necessarily affect the way in how the ledger state is updated. Obviously, the more and more nodes and bad nodes that get into that pool could lead to the possibility of pollution and potentially a double spend, but the research that we've been doing has led to like a 0.01% probability over 1,000 given years of actually being able to pollute that ledger state update. But when that does happen, it's sad banana. So yeah, this is some of the 51% attack research that we've been doing on this. We built a lot of simulation models, tested lots of different constitutions of networks, lots of different scenarios of given, if you have a validation pool of a given size with this given number of worker nodes, reservist nodes, bad nodes, ledger times. But we actually came to a very strong percentage of confidence that every state update will be valid. This research is published on our GitHub. To get access to this, we are running an early access program at the moment. So if you'd like to actually get access to this research, please come and see us afterwards. We'll happily let you in. So I talked about the ledger cycle and how producers have to validate a common set of transactions from the mempool, and each producer compiles a state delta and votes among its peers in that cycle to vote on the most popular delta produced by that set of producers. So this is actually a more complex view of what our ledger cycle update looks like. You can see here we went through the creating of a transaction, broadcasting it, validating it against our rules, and then actually the nodes producing that vote of a delta state update. Once a state update has been actually produced, the nodes, like I say, will actually then, among themselves in that producer pool, they will vote on the most common, the most common agreement of an update. So, as I said earlier on, some nodes may not receive all transactions, and they may come to a different outcome on what that update is. But because it's a vote on the actual next state update, that if there is any discrepancies because you haven't received the same number of transactions or the evil nodes producing bad updates, that this voting phase of the update cycle actually filters out any of that noise. And once they've come to an agreement, the new state update is broadcast into the DFS. DFS hash, as we said earlier, is broadcast to the rest of the network. They pull out that state update from the file system, and they update their ledger, and the global state is been updated. So again, this is an actual full-on ledger cycle update. These are all the phases that we've kind of just gone through again. The construction phase of a state update being computed and broadcasted to all the other producers. The campaigning phase, which is the nodes voting amongst themselves in that producer pool to actually vote on what they say is the next state update. And the synchronization phase, which is, as I said, them actually broadcasting that state update to the rest of the network and then building up their new state for that cycle. So that's kind of like the high level of the consensus algorithms behind what is a probabilistic BFT. Please do come and speak to us if there's any of that was unclear. So next, let's talk a bit more about the actual code and what is involved in Catalyst itself. So Catalyst is really what we've been building is a core framework. We don't just give you one specification and say you have to use it. Like I said earlier, we've tried to aid the adoption of Catalyst and ledgers in businesses by making it very modular and flexible. So you don't necessarily have to take all parts of our system to use in a business use case. You can just take bits and pieces of this. So the core framework itself, the architecture looks a little bit like this. On the very base layer, we have the Catalyst protocol, and that is a abstract agreement of messages and rules of how nodes should interact with each other on that network. The next layer up, we call like the protocol SDK layer, and the Catalyst protocol itself, these agreement and messages are written in protobufs, so it's a serialization format by Google, which is a abstract format. I mean, we just looked at it earlier on. This is actually what a protobuf message looks like. Just, it tells you the kind of data, the name of the field, the actual data type, and the actual order of them fields that get broadcast as bytes across the network. Google are very smart and figured out a way of actually being able to cross-compile all these into multiple different languages. So as it stands now, we actually support lots of different languages in terms of SDK development. Obviously, well, not obviously, but the core code base is written in C#. That's the main implementation, but we have SDKs for JavaScript, Java, Go, Python, Ruby, you name it, pretty much as an SDK there for people to start getting started and actually developing and building on Catalyst. On the next layer up is the Catalyst core lib, and this Catalyst core lib is, again, a very low-level library which contains I/O network operations, file system operations, cryptography, key signers, key stores, very basic but important aspects of a distributed ledger that are needed to run. On the next level up, we have the Catalyst core modules, and there's a star there because there's multiple core modules within the system that actually provide the flavor of a node and the functionality of a node. There's some core modules that must be included to actually constitute as a working node on Catalyst, but there is additional modules like the Catalyst modules on top. That can provide custom flavor. So, for example, earlier when I was saying about how we can run DNS, or we can run certain APIs for Web3 interfaces. These are kind of optionals. You don't require to run them to actually be able to achieve consensus. And then we have custom modules. So again, the modular and plugin architecture of the system allows you to then extend that functionality to be able to provide any other types of functionality for a business use case or for fun. In the next part, we actually have some examples of a custom module that we built that can provide a Twitter functionality over this. So yeah, Catalyst core protocol, the SDKs, the core libs, the modules. So these are the core modules that are fully required to actually constitute as a node on the network. The KVM module, as I said earlier, the virtual machine that we have, the consensus module, which we discussed earlier in that ledger cycle update. The actual ledger itself, which is actually the data object and the global state object that holds all your account information, all your smart contract information. The deterministic mempool that we discussed. The key signer. Key signer is essentially a wallet, signs your transactions, signs your messages on the network. Key store keeps your keys safe. The cryptography module, which includes our bulletproof and range-proof private transaction implementation, and the distributed file system module as well, which contains that global file storage for everyone to use. As I said, yeah, the custom modules can provide real domain-specific functionality. So this is kind of an example of how you can assemble these modules into a node. And this is our first distribution or our first flavor of a node, which will be released in the next month or two. And this is Catalyst Node Proof of Authority Community Edition. So what we've been working on is our initial distribution is a subset of these core modules. So without the KVM initially. But what we actually did was we built a POA consensus module, which actually uses a lot of the underlying Delta state updates that we discussed earlier. The only difference between the POA consensus and the final consensus is that only the authority nodes are allowed to actually produce that global state. And a POA discovery, just to show that how you can extend all the underlying modules and the core libs to really provide like custom functionality. And the final version that we'll be releasing of Q1 next year is the full Catalyst node community edition. And this features all the core modules, as I discussed earlier, with the KVM. But this will also include the distributed compute. And the distributed compute, as I said earlier, is kind of a more complex, feature-rich environment to do computing on blockchain, rather than just having a global state machine like the KVM, where you can do limited kind of functionality. On distributed compute, you'd actually be able to run pretty much any type of computation. You could even potentially migrate existing applications. That distributed compute works in a very similar way to how AWS Lambdas or Azure functions work. So you'd actually be able to call that with data and have long-standing computation happen, and then the distributed compute will actually feed back into the consensus, the output, and give you the truth of what that computation was. The Web3 module, kind of is, again, provides the backwards compatibility with Ethereum. So anyone who's been building on Truffle, there'll be backwards compatibility with that, plus additional functionality that covers all the Catalyst core modules, and the distributed DNS. Distributed DNS, again, that can link to any kind of content. So you could link to content on DFS. You could link to wallet addresses, so you could actually take payments like james@catalyst.cat, rather than having to remember really long arbitrary strings. So I mean, I've talked about KVM quite a bit. KVM is the Catalyst virtual machine. We're actually working with a company called Nevermind in London. I don't know if people have heard of these. Nevermind are an Ethereum client, essentially, an Ethereum studio. They've got one of the fastest syncing clients built in .NET Core again. So we're working with these guys to actually provide a backwards compatibility and a backport from EVM, but actually add in more functionality, so you'll actually be able to pragmatically access the DFS, which will allow you to pay for file storage, pay for file retrieval, pay for the distributed compute. We'll have compatibility with all the previous ERC standards, so the ERC 20, 223, and 721. The EVM compatibility will allow existing solutions that already work on Ethereum to be ported over to Catalyst for stuff like Uniswap and MakerDAO, and a bunch of other DeFi tools. Yep, the backwards compatibility, as I said, with the Web3 module. You'll have the option of using JSON RPC or Protobus to interface with that API. The KVM will provide native access to DFS. Cryptography. Also, the KVM itself will have a bunch of new precompiles added into it, so you'd actually be able to use our native range proofs and cryptography libraries within the virtual machine, so you'd actually be able to do confidential smart contracts logic within there as well. And I mean, there's lots of things wrong with the EVM as it stands, but since we're taking it from an absolute fresh stance and you have no existing people using it, it's quite easy for us to, at this moment in time, rectify lots of things that are wrong with the EVM. So obviously the biggest problem with EVM is state bloat, where people have produced contracts and just left them there and dumped them in the blockchain. Over 1 terabyte now of just a lot of that just kind of worthless smart contracts that are no longer being used. So we're actually working on a state rent mechanism. That state rent mechanism will actually allow smart contracts themselves to pay for hosting within that global state. Once you've stopped paying for your place within the global state, you'll be evicted. So this is actually a way of combating a lot of that state bloat that we see already in the existing EVM models. So this is kind of just like a brief overview. Like I said, if you want to come and speak to us afterwards, come and speak to us. We've got an early access program. We're really looking for developers who are interested in core protocol development on .NET Core or any other languages. We're also looking for lots of people who are interested in building tooling or proof of concepts or demo applications on this. And yeah, follow me. I'm on Twitter. I'm on GitHub. That's all. Thank you.